Welcome to our beautiful, high-definition tour of thermodynamics. We will build an intuitive picture of heat, work, energy, and entropy, and then solve a concrete example you can reuse on tests and labs. Thermodynamics starts by drawing a boundary. Inside is the system, and outside is the surroundings. Energy can cross this boundary as heat and as work. If heat flows into the system, we call it positive heat. If the system does work on the surroundings, we call that positive work by the system. The Zeroth Law of Thermodynamics defines temperature. If object A is in thermal equilibrium with object B, and B is in thermal equilibrium with object C, then A and C are in thermal equilibrium. In practice, put two objects in contact and wait. If there is no net heat flow, their temperatures are equal. Now, the first law of thermodynamics is a statement of energy conservation. The change in internal energy equals heat in minus work out. Delta U equals Q minus W. Sign convention. Q is positive when heat enters the system, and W is positive when the system does work on the surroundings. Here is the most useful mental picture. A gas in a cylinder with a movable piston. Add heat and the gas can expand and push the piston, doing work. Remove heat or push on the piston, and the gas can be compressed. Watch the piston move as we add and remove heat. A pressure-volume diagram shows pressure on the vertical axis and volume on the horizontal axis. The work by the gas is the area under the curve. We will draw an isothermal curve and an adiabatic curve for comparison. Let us compute a concrete example you can use on homework and labs. Isothermal compression of 1 mole of an ideal gas at 300 Kelvin from 10 liters to 5 liters. For an isothermal ideal gas, the change in internal energy is 0, so heat equals negative work. The work by the gas equals N, RT times the natural log of V2 over V1. W by gas equals N, RT log of V2 over V1. Plug in N equals 1 mole. R equals 8.314 joules per mole Kelvin. T equals 300 Kelvin. V2 over V1 equals 1/2. The natural log of 1/2 is negative 0.693. So the work by the gas is about negative 1,730 joules. Because the process is isothermal, heat equals negative work, so about positive 1,730 joules of heat must be removed from the gas during compression. The second law introduces entropy and explains the direction of processes. Heat naturally flows from hot to cold, and no engine can be perfectly efficient. A heat engine takes heat from a hot reservoir, dumps some heat to a cold reservoir, and converts the rest to useful work. Its efficiency is work out divided by heat in, and is at most 1 minus T cold over T hot. Entropy measures energy spreading and the number of microstates. In a reversible heat transfer, the change in entropy equals heat over temperature. Delta S equals Q, reversible divided by T. For any real process, the total entropy of the universe increases or stays the same. Today, we built an intuitive visual toolkit for thermodynamics, system and surroundings, the first law with heat and work, pressure volume diagrams with work as area, and the second law with entropy and engine limits. Keep these pictures in your mind, and the equations will make much more sense.